to the channel. Hope everyone is having a great day. Today we'll be looking at a problem on LeetCode called Unique Paths 2. And if you like and want to learn about data structures and algorithms, please like and subscribe and follow me on Twitter and share with anyone else you might think will like this content. Without further ado, let's learn something epic. Alright, so it looks like this problem says there's a robot located at the top left corner of n by n grid marked start in the diagram, and the robot can only move down, right, at any point in time. The robot is trying to reach the bottom right corner of the grid marked finish in the diagram below. Now consider if some obstacles are added in the grid, how many unique paths will be there? Tells us obstacle and empty space marked 1 and 0 respectively, and m and n will be at most 100. Okay, so we take this example and we see that one path you could go right and then move down and then you end up there. We start here, another path is there. Move down this column and then move to the right all the way to the end, and that's our second path, and they explain it as well. One thing for this problem is it's easy, for me at least. I was quick to think that DFS could solve the problem, because DFS is usually used for exploration, but one thing to consider is for DFS, since you need to get all paths, if we look at this example, you would have to go right. One path is you go right, and then you go, let's say you go right once column, and then you travel down this column, and then you make a right here. So that's one path. But then another traversal for this node would be to make a right here, and then to go down here. And what this illustrates is that normally in DFS, once you traverse a node, you mark it as traverse and you never traverse that point again. But we see here that just because you find a path here moving right and then going down, doesn't mean you can mark this node as traverse and never traverse it, because you could also traverse down and move right from this node that I marked with a star. So we have to throw DFS out the window. What we can do, however, is we can employ a dynamic programming approach, because we know that the robot can only move either down or right at any point in time. It also means that any position can only take paths from two other positions. So here we draw up an example. Let's take the example that we have above. So we know this position, all the possible paths have to start here. So if it's 0, we know we'll make a second matrix for the DP. So this is the original matrix, and this is the DP matrix. Yeah, so as I was saying, for this position, if it's 1, if there's an obstacle, for sure there's no solution, because there's no way you can start in that position and end up in the finish. However, if it's a 0, you know that it'll always have the potential to be part of a path, so you mark it as 1. Then we traverse to this point, and we check, because the robot can only move down or right at any position, we check where the possible paths can come to that position. So that means if it can only move down or right, we would check left and top. So if we check the left, we see that there's a 1. Okay, so we say it could be 1 plus whatever is in the top, and there's no top, so it's plus 0, so it remains as 1. At this point, we do the same. Check the left, check top. There's no top, so that's 0, so 1 plus 1. 1 plus 0 is 1. And then we move on to this point. So there's no left, but there's a top, so left is 0 plus 1, and we end up with 1. So now, the DP should have initially all been zeros. Now for this point, we know that it has a 1, which is an obstacle. So that means this DP, we would not sum the paths of left and top because there's no possible path that can be made, including this point. So we advance, and then once we reach this point, we see in the matrix it is a 0. So that means that we can sum the paths of the left and the top. And so that would be 1 because left we have 0 and then top we have 1. Now we move to this point. Similarly, this is 1 and this one's also 1. And when we end up here, we sum 1 and 1 and we get bam, 2, and that's the output. And so I hope this illustration can help you see how our solution can be. Now I'll summarize in words. Basically, make a DP matrix, same dimensions, then fill first position with 0 if first position, let's denote it with 0, 0. If matrix equals 0. All right. Iterate DP, iterate elements of matrix if element is 0, sum left and sum top from DP. Else continue because we are not filling that element for DP. And in the end, we will return the bottom right corner because that is the end position. All right, so that's our main idea and some pseudocode. The runtime of this algorithm, because we're iterating through each of the elements, it will be, let's say we have m rows and n columns. Runtime is O of m times n because you have to iterate through each of the elements. And each time we will be summing the left and summing the top, and that will cost a constant of 2, but in big O we ignore constants. So even though it's O2 m times n, when we have big O notation, we will drop the constant. So it'll be O m times n. And then space complexity is O m times n as well because we need to make the DP matrix. All right, so we have our main idea, we have our pseudocode, and we have our pseudocode and our runtime space complexity. So let us continue and type the code. So let's see, row equals length of obstacle grid, column equals length obstacle grid 0. So let's see, if I find length obstacle grid, I get 3. And when I take in this example, I get 3. And so the row, let's do -1 because it's 0 indexed in Python. So 0, 1, 2 would be in bounds. And then for the column, it would be -1 as well. Same reasoning, 0 indexed. Now we make the DP matrix. So DP equals 0 for I in row. Make the rows first, and for j in column. Let's see if that syntax is correct. So that's compile error. Oh, okay, it's because of this stuff. Yeah, I'm not too sure about the syntax, but we can check that quickly here. 7. Right, so I need range as well because I'm iterating through the rows. Same thing for column. So what I think this should do is, oh, okay, this might need to be columns. Let's try a 3 by 2 so I can figure out what the rows and columns should be. Okay, great. So, okay. So it looks like I have 2, and I put that in the columns, but that should be reversed. So it should be row and then column. And we see that in Python, the +1 should be there because when row is 2, it will do 0, 1, but I actually wanted to do 0, 1, 2. So let's see if this one matches, and it does it. So that means the rows and columns should be switched. All right, great. So now the DP matrix looks good. We continue and fill the first position. Well, we have to first check if obstacle grid. I like to call it matrix. It makes it a little bit easier. Less typing. All right, well, we would have no solution if that's the case. Otherwise, we set it equal to 1, and then we iterate the matrix. And row is 2, so it actually has to be row plus 1. Goes up to 0, 1, 2. All right. If matrix is equal to 1, if it's equal to 0, we can sum the left and the right. So yeah, so the left one, well, we have to check if it's in bounds. So I is greater than 0, so we're actually checking the current element in DP, and then we are summing that with the top element, and then if j greater than 0, dp j is equal to dp. Yeah, so now we sum the left element, so we're actually doing top and then left element. And we do that only if it's equal to 0. Right, now we have our else case. Maybe just uncomment. Row minus 1, column minus 1. Because I already subtracted 1, I don't need to subtract 1 again. Okay, now let's run through our example to make sure it looks good. So we have our matrix 0, 0, 0, 0, 1, 0, and we get the length of obstacle grid, which is 3. subtract 1, so now it's 2. Same thing with column, so now we have 2, 2 for row and column. And then when we do the range, it's plus column plus 1 and row plus 1, so we get a 3 by 3. All zeros. Now we make matrix equal to obstacle grid, so I don't have to type as much. Obstacle grid, obstacle grid, obstacle grid, row, column. Yes, I made the range mistake, but I typically catch it with the error message. So we check if the matrix equals 1 in the first position, we return 0. It is not. So then we make dp first position equal to 1. And then we go through, iterate the matrix I in range, row plus 1, j in column plus 1. So row and column is 2. So that means I go through 0, 1, 2. So with 0, 0, looks like I'm going through 0, 0 again. And then I'm checking if it's 0, and it's not, so I continue. And then now I'm on 0, 1. So 0, 1, it is a 0. So then I sum the left. 0, 1. But 0 is not greater than 0. So we go to the next if statement. And then 1 is greater than 0. So then we would check the left one. So we'll check 0, 0 plus equals. So we get 1. Now we're on 0, 2. When we are on 0, 2, we check 0, 2 in the matrix, and we see it's a 0. Then our dp 0, 2, 0 is not greater than 0, so we go to the j. 2 is greater than 0, so we check 0, 1. And the value for 0, 1 is 1, so we add that to our matrix. Bam, we got 1. And now we're on 1, 0. So on 1, 0, we check our matrix. It's a 0 with this if statement. Then 1 is greater than 0. So now we have to do I minus 1. So 0, 0, 0, 0, 0 is the value. So we add that, and now we get 1. And then for j, since it's 1, 0, j is 0 is not greater than that. So yeah, we move on. So now we're on 2, 2. Now we're on 1, 1, and in 1, 1 we don't have a 0, so we continue. And then now we're on 1, 2, and 1, 2, both of them are greater than 0, so both these if statements will work. So the first one is we check 0, 2, and that's a 1, so we know we have to add 1. And then we have, because it's 1, 2, I'll also look at 1, 1, but that's 0, so it's 1 plus 0 equals 1. Now we're here, 2, 0. On 2, 0, we see that I is greater than 2, or I is greater than 0, and so we would look at 1, 0. So we add 1 is at 1, 0, and that's a 1. And then 0 is not greater than 0, so final answer is 1 in that position. Now we're at this position. So we are at 2, 1, and at 2, 1, we check our matrix 2, 1. Okay, it's a 0, so we continue, and then we see that, well, both I and j are greater than 0, so we'll execute both if statements. And so at 2, 1, we'll look at 1, 2, and it's a, 1, 2, I meant 1, 1. So at 1, 1, we have a 0, so it's 0 plus. We're at 2, 1. So then now we have to look at 2, 0, and that's a 1. So our last answer is 1. And now we find at the last position, so 2, 2, we check our matrix 2, 2, and we see it's a 0. And then 2 is bigger than 0. So then our position we will update with 1, 2, and at 1, 2 we have a 1, so 1 plus. And then at 2, 2, j is also greater than 0. So we will look at 2, 1, and it's a 1. So now we have a 2 at that position, and then return the last position, which is 2, 2, row, column, and that is the correct answer. So let's try this custom case, see if it works. Okay, so we have compile error 24. Is it because of the example? Or? I see. Should have been equals, not setting it in the if statement. (32) indentation. Huh. That's interesting. Well, they want me to type it 4 spaces the entire time. Expected and indented block. Oh, I see. It has to be within the for loop. Alright, so let's see if this makes sense. 4, 4, 4. I'm going to put the if inside, this if inside, and this. Yeah, these are inside the ifs, this on the outside the else. Okay, so that one looks good, but just out of curiosity, what if I did not have this island? Let's see the paths here. Also wondering if the empty grid has to be taken into account. We'll see. Nope, looks like that is fine. Awesome. Well, that's it for today. I hope you guys learned as much as I have and had as much fun as I had as well. Hope you all have enjoy the rest of your day, and like and subscribe if you want similar content.